Hello, this is Mr. Gilmore with the 3.3 Part 3 Pons Asinorum lesson. Now we're going to take a look at how Euclid proved the isosceles triangle theorem. We actually have a convenient postulate for us that Euclid didn't have. See, when we tackled the isosceles triangle theorem, we were able to bisect an angle because we have the protractor postulate. But in Euclid's time, they didn't have the ruler postulate or the protractor postulate laying around to help them. No, Euclid had to tackle the proof quite differently. In fact, if you're curious, you can hop over and take a look at the elements that I have posted on Canvas. In the elements, you're going to look at proposition number 5. This is where Euclid proves his version of the isosceles triangle theorem because he was not able to construct angle bisectors. In fact, if he wanted to prove the use of angle bisectors, he actually needed the use of the isosceles triangle theorem to do that, which means he could not have constructed an angle bisector to prove his isosceles triangle theorem because he would have created circular reasoning for himself. Now, your eyes do not deceive you. There really are only 2 slides here. On the next slide, we're going to take a look at what does Pons Asinorum mean. Well, Pons Asinorum is actually a Latin phrase describing the type of proof. And more literal translation, we'll look at that here in just a second. More literal translation is a little bit of a naughty word in it. So let's take a look at what is Pons Asinorum. This is called the bridge of asses. This is actually how that word literally translates, Pons Asinorum. So the bridge of asses, and here's why it gets its name. What Euclid does is when he's given himself an isosceles triangle to work with. So we originally start with triangle ABC, given that AB and AC are equal to each other. But part of his constructions that he does on the diagram, it actually takes the triangle and it transforms it to make it look sort of like a bridge, which is where we get the bridge name from. Now, why do they call it the bridge of asses? Because here's what happened. There were a lot of pupils, a lot of students that wanted to come and study underneath Euclid and his works in mathematics. Well, when they jumped in, they started to grasp geometry pretty well, right? Oh, the very first proposition, not too bad, got that. Proposition number 2, got that, not too bad. Proposition number 3, proposition number 4, all of a sudden they get to this proposition on the isosceles triangle theorem. And it's not as easy as it seems. It's actually quite difficult, which really this bridge of asses would pretty much translate more to be like the bridge of fools, because people were deceiving themselves thinking that they really understood Euclidean geometry, but however, they could not cross the bridge. They could not get across it because it was really quite difficult. And so this bridge of asses separated those who could do geometry and those who couldn't. And so we're going to see, I'm going to leave this proof up to you guys to figure out on your own. Now, I've gone ahead and helped you out a little bit, okay? I've gone ahead and helped you out with what the constructions involve. Yes, Euclid was allowed to construct, okay? So we can extend segments, right? We can extend segments, we connect points. All those are allowable constructions that we have, as well as what Euclid had. So here's how he does it. He extends both of the legs of his isosceles, AC and AB, through to a point D on AC and through to a point E through AB, and in such a manner that CD and BE are equal to each other. So notice that I have the double hash mark on the segments CD here and the segments BE here. Okay. Now, we already know then a few things about our diagram. We're given that AC and AB were equal, okay, and now we have CD and BE are equal. Here's a little bit of a hint. What happens if we took equals and added it to equals? What if, again, we had these equal things and added them to equals? There's a little bit of a hint there for you. Now, your last hint that I'm going to give you to help you cross this bridge of asses is this. You're going to be looking for congruent triangles. In fact, you're going to be looking for 2 pairs of congruent triangles. Let that be your guide. 2 pairs of congruent triangles. And you're going to then discover how you're going to be able to prove that angle ACB and angle ABC are equal to each other. That's your goal. Show that those 2 angles are equal. Alrighty? If you do have any questions, do not hesitate to ask me. But other than that, be good and do good.